All right, welcome to lesson 5 on using matrices to organize data and solve problems. You have a warm-up to do in your notes, so go ahead and do that, and then we're going to start off with some vocabulary. Couple of vocabulary terms for you, just a few here. And the first one is a matrix is an array of numbers, and you'll understand what that means in a minute. And this array of numbers can be used to store or represent data that we normally would represent in a table. So the elements, there are elements in each matrix, and those elements are the individual pieces of data in the matrix. This will all make more sense when we look at examples. So for now, just get the definitions down. Matrices are named using a capital letter, and there is also a subscript that indicates the number of rows and columns, and the rows are always first and the columns are always last. So we name the elements using lowercase letters, and they also have a subscript that identify their location, again, it's row by column. So let's go ahead and get into some of this. Here's an example. Here's matrix A. Notice it's a capital letter. Matrix A is a 3 by 2 matrix. We give the number of rows first. They are horizontal. Columns are second, and those are vertical, so that's why it's 3 by 2. There are 3 rows, 2 columns. So the way we label matrix A is A sub 3 by 2. Okay, and that's just how you label it. 3 by 2 gives us the dimensions. A is the name of the matrix. So as far as the elements go, all of the elements in the matrix have a location, and they are labeled by their location. Just like the matrix is row by column, each element goes row by column. So this subscript says the element 3 is in row 1, column 1. Element -4 is in row 1, column 2, and so on and so forth. So how do we add matrices together? Well, it's really pretty straightforward. All you do, they have to have the same dimensions to add the matrices together. And all we do is we add the elements that are in the same position. So the commutative property is true for matrix addition. It doesn't matter what order. If I put matrix B right here in front, I'll get the same result as if I put it second. So the order does not matter when we are adding matrices. How about subtraction? Does that matter for matrices? Does the order in which we subtract matrices matter? Whoops, not sure what's going on there. And it works out that it does matter, okay? So matrix subtraction is given as A plus the opposite of B. That would define A minus B. Now matrix subtraction is not commutative. Okay, so if we're going to subtract matrices, again, we go left to right and we subtract the elements that are in the corresponding locations by adding the opposite. So A11 minus B11, we're going to say that's A plus the opposite of B11. Here are some examples. So it says use the data in the tables to create 2 matrices. And then we're going to find the sum of those 2 matrices. Okay? So matrix C, first of all, we'll start by writing matrix C for the Center City store. Matrix C is equal to, this is a 3 row by 2 column, and here are its elements, 1250, 1893, and 2388. And then column 2 has these elements, 1340, 2455, and 3674. Okay? And then matrix N has these elements. 985 is row 1, column 1, 1987, 1582, and then column 2 is 1020, 1765, and 2001. So there you have the 2 matrices. So then the problem said, find the sum of those 2, right? It said find C plus N. So all we're going to do is we're going to add those two matrices. So let's do that in black, I guess. So C plus N, let's extend our page here. C plus N, we just add those elements in the same position. Here's where I need my calculator to work for me. So we're going to add 1250 plus 985, and we end up with 2235. And then we're going to add 1893 and 1987, right? And we get 3880. And then 2388 plus 1582. And I got 3970. And then over to column 2, we have 1340 plus 1020. And I get 2360. 2455 plus 1765 gives us 4220. And please let me know if I've done any of these additions incorrectly. I'm going kind of fast here. 3674, add to that 2001. And I got 5675. So there's our matrix addition. Find the additive inverse of the matrix. Well, in this one, the additive inverse, let's say we call this matrix A. The additive inverse, we want matrix A plus another matrix I'll call X. We want that to give us the identity. The additive identity is 0. So this matrix X is what we're looking for. And what do I add to a number to make it add to 0? It's just the opposite. So X, matrix X, is just going to be the opposite of A, right? So all we're going to have to do is say, okay, well, that's just everything with an opposite sign. 0, -1, -4.5, +1, +5, -12, -21, and -2.5. So that would be our inverse, additive inverse matrix. To find a subtraction here, basically remember all we're going to do is we're going to change this to addition, and we're going to change the signs inside every element here. That's going to be minus, that'll be plus, that'll be plus, that'll be minus, 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 and minus. And then we're just going to use addition. So our resulting matrix, 2.3 minus 4.3, is minus 2.0. Minus 9 plus 0 is minus 9. 1 minus 25 is minus 24. 0 plus 6 is 6. Negative 45 plus negative 10.5 is negative 55.5. 17 plus a negative 10 is 7. Negative 8 plus 14 is 6. 7.2 plus a negative 6 is 1.2. Negative 15 minus 30 is negative 45. And then put your square brackets around each side so that you know it's a matrix. To solve for x, let's call this first matrix A. And then we have x, A plus x equals, and let's call the one on the right B. If we want to get x by itself, what do we have to do? We need to add negative A to this, right? And whatever we do to one side, we have to do to the other, plus negative A. So I'm going to add those two and say that x equals negative A plus B, right? So what is negative A? It's this matrix with its signs changed. So x is equal to negative 12, 3. So that's the opposite of matrix A. And we're going to add that to matrix B. And B is negative 7, 0. So when we add those together, our matrix X is equal to negative 12 plus negative 7, which is negative 19. 3 plus 0 is 3. And there's our answer. All right, on this problem, we want to solve for A, B, C, and D. So if these two matrices are equal, that means all the elements in the corresponding positions must be equal. So we can say A plus 1 equals 5. subtract 1 from both sides, and that tells us that A is equal to 4, right? So we've solved for A. Over here in the B position, it says 14 has to equal B. Well, that's already solved, so we're done with that one. Down in row 2, column 1, it says C equals B minus 2. So write that equation. But now you know that B is really 14. So C equals 14 minus 2, which is 12. 1 to go. The last one says D equals half AB. Well, we know both A and B now. A is 4 and B is 14. So that's what D is equal to. Half of 4 times 14, which is 28. So D equals 28. Scalar multiplication. So scalar multiplication, a scalar is basically just a number. It's a number in front of a matrix. It has a magnitude. Maybe in your science or physics class you've talked about scalars versus vectors. Scalars don't have direction, they are just magnitude. So a scalar is just a number that you multiply. And to do that with a matrix, you just multiply every element in the matrix by that number. So this problem, I'm not going to take the time in this video to do this because this takes a little bit of time. I want you to go ahead and set this up. Call this matrix on the left matrix A. Okay, so maybe make this right here matrix A. And then you're going to call this one right here matrix B. Okay, and then they want you to find this amount. Okay, 3A minus 3 times 0.75B, and figure out which is the better deal. So the other comment that's in here in the little bubble, what does that represent? Well, that represents the better deal. So see if you can do that one on your own, and we'll talk about it in class. See you next time.